Gabe, we're glad you're here today and look forward to your presentation. Give us some background on who you are, then take over.
Absolutely. No, thank you everyone for the very warm Dallas welcome. My name is Gabe Prado and I'm a product marketing manager for SparkCognition. We're an AI company based out of Austin, Texas, so just down the road you'll find us in Austin. And I'm really excited to be here to chat a little bit about AI. So I know there's a lot of buzz in the industry about this, in this space about AI, machine learning. And we have such a wonderful representation of backgrounds here in the room. So my intent is to provide some nuggets of knowledge of machine learning and kind of where we're working on within the umbrella of AI, and then spend some time towards the end on just starting to cover some of the applications and some of the ways that you can start thinking about projects and how to apply AI to some of those projects. Now first, a quick bit of housekeeping. I actually have 3 of our CEO's book. He just released The Sentient Machine. I've got 3 signed copies here. So I'll be passing around a paper bag. Feel free to drop a business card in. To be honest, it's a really compelling read. It paints a really interesting picture of the future. Our CEO has been working on, has been thinking about machine learning and artificial intelligence since he was a kid, since he saw his first computer. So it's a really interesting read to see how his vision is playing out, and some of the problems and the solutions I will have here in the future. Now, just to kind of get started here, I wanted to understand if there are any burning questions about AI. If you came here with a really important question, I'd love to uncover some of that now, write it down, and try to address that during the presentation. But are there any particular questions or any burning nuggets of knowledge that you're trying to get out today? Well, then my job is easy. Thank you guys. I'll see y'all tomorrow. But let's just take this back to kind of the history of modern AI, right? Where did AI start becoming a concept? Now let's go all the way back to the 1950s. And you guys are probably familiar with some of Alan Turing's work, but this is where we start to see the concept of machines thinking like people. And you might be familiar with the Turing test, where a human operator is asking questions to a machine and a human, and trying to understand when it's a machine that's giving the responses. So this is where we start to see this concept of AI start to play out. And it's formalized as a term in 1956 with John McCarthy. He kind of coins AI, artificial intelligence, as a way to define some of the science of machines thinking like people. Now we fast forward to the second revolution of AI, AI 2.0 in the 1980s. And as computing power continues to take off, we start to get this understanding of AI as a way to, AI as expert systems, which can start to solve problems in a very logical fashion. And then we fast forward to close to where we are today, to the 2000s, where we finally start to see deep learning take off, and this complicated approach at really mimicking how a human brain interacts and is able to solve problems and start to translate that to machines. So it's definitely been an evolution. Now, artificial intelligence is a very broad umbrella, right? There's a lot in this, but for simplicity, we'll look at two of these different disciplines. On one hand, you have artificial general intelligence, and this is what a lot of people think of when they think of AI. They think of robots, they think of computers and systems that are able to basically solve any type of problem just in a similar way that a human might solve that problem. Now, we're not quite there yet. Where we are right now is relying on this domain of expert systems. And like I said, these expert systems are considered them somewhat of a domain expert. So they have it's a computer or a program or a machine that can solve problems within a very focused domain. So think of it almost like a domain expert, but instead of human processing, it's a machine that can solve problems within a very tight task area. Now, while AI is really only 60 years old, it's kind of crazy that in the next century, we will have made this jump from expert systems to AGI. A lot of experts are believing, I have a high degree of confidence that we're going to reach AGI in our lifetimes, and that's really exciting news. Now, a little background on why we got to where we are. Why is AI such a big deal right now? And it really comes down to 3 things. First, there is just the compute power, right? Moore's law, things have gotten much cheaper. We've got the GPUs available, we've got the processing, the server rack, we've got the computing power necessary to handle some really complex systems. And then we're also sensorizing everything, right? We have more data than we've ever had it. This is sensor data, or it is data from documents, and we can start to use that data to paint a picture and apply machine learning to extract some really important insights. So we've got some sensor people here in the room. I've heard little bits, but these two things combined with the advancements in the science behind AI and where we are from an algorithmic and model building perspective, those three things come together for a perfect storm, and is what is driving the success of AI and where we are right now. And you can see AI all over the place, right? We're using it to drive self-driving cars. It's an IBM Watson. You know, it's how you interact with Siri and how you can do predictive texting. We use it in the industrial space, and then at the same time, Google is using it in a host of applications. So, does anyone else have any other examples of where they've seen AI or where they're using AI currently?
Call bots.
Yeah, absolutely. Absolutely. So good and bad.
And all the natural language processing, we had a session.
Yeah. Yeah, absolutely. So a lot of different applications here. Now, if we go back to the diagram of AGI versus expert systems, we can follow this path down a little bit more and start looking at like natural language processing. I'm not going to spend as much time about NLP, but for those that are unaware, natural language processing is basically looking at text, through PDFs or emails or any unstructured types of data and able to read them and extract insights just like a human would from that type of data. But I'll actually spend most of my time talking about machine learning. This is where SparkCognition is really placing their bets here on machine learning and NLP. Now, machine learning consists of neural networks and learning algorithms and models. So I know there's a diverse set of backgrounds here, so I'm going to spend a little bit of time just kind of going into algorithms, models, model building, and then move into some application spaces. So again, more examples. Machine learning is everywhere around you. Netflix uses it to make recommendations. Facebook drives news to your newsfeed and to write friendships. Google Mail, Watson is using it to do some stuff, and then Google is using it for driving cars. So the applications for AI are truly all around us. Now let's take a quick example here. So let's say you've got a collection of fruit. How would you write the code to tell these fruits apart? Now on one hand, the obvious human shortcut is to look at this based on color, right? Bananas are yellow, apples are red, grapes are green, and that would be one way to write the code to separate these. But that's not always the case, right? A lot of times there's more ambiguity, there's more variables in play, and so you've got yellow apple, you've got different colors, so this algorithm isn't perfect, or this code wouldn't be perfect just based on color. So at a high level, what machine learning does is it takes the heuristics out of the picture and kind of flips it on its head, and basically looks at all the different characteristics of a set of items or a set of data, right? So when humans might take the shortcut to look at things just based on color, machine learning might look at all the different variables on how to actually classify this group. So look at height, width, color, and shape. And because of the processing power and because of the ability to look at all of this in a very short amount of time, can get to a much higher degree of confidence in sorting those fruits into the right items. Now, at the heart of machine learning is an algorithm, right? Now, an algorithm, a simple definition of an algorithm is just it's a set of steps or it's a set of rules designed to fix a very particular type of problem, right? So I hate being left in the dark. My wife hates it as well. A lot of you guys probably have lamps at your house. So what do you do when your lamp doesn't work, right? You can start to think about fixing this problem as a type of algorithm. First check is, all right, is your lamp plugged in? Does something else take the plug? What do you do? If that's the case, let's plug in the lamp. That's the easy fix of the solution. Let's say it is plugged in. All right, the next step is to check if this bulb is burned out. So next logical rule to follow based on the criteria. All right, so maybe you have to buy a new lamp, or it could be as easy as just replacing the bulb inside that lamp. So now there's a way to start to break down a complicated problem to a series of steps designed to efficiently solve that problem. Now we get more into the model building process. So once you have data, and once you have a learning algorithm, you can combine these two together to start building predictive models. Now, much like you have like a model of a ship or an airplane, you've got a decent representation of what the big ship or the big airplane is without having to need that physical thing there. So a model is used to characterize a set of data and start to make predictions about similar types of data sets. And the power behind this is that the machine, when you combine this together with a machine learning algorithm, you can build this model that starts to learn over time and starts to without explicitly being programmed, starts to get better at its job. And that's the true power of machine learning there. Now, for a model to work, it typically has to be trained in some type of way. There has to be a set of training data that this model is exposed to so that it knows what inputs and outputs. And there's two key categories on how to typically train a model. On one hand, you have a supervised approach. And this is where the inputs of that data map to the outputs. We know the inputs and the outputs, and it's up to the algorithm to figure out how to sort that itself. So like a good example here, let's go back to another fruit example. Say you have a bucket of apples. Each apple has a number and a different color, and your goal is to sort those apples into the right color. Now because you know where those apples should end up, you can run this through the algorithm and see how it sorts the first time. But it may not be perfect. So you iterate on this again, you run it through the algorithm again, and the algorithm gets a little bit better. So eventually, after the iteration, after several iterations, you get to a point where this model can accurately sort everything based on that set of training apples, if you will. Then you can use that model to run new apples through the algorithm and see how it classifies those as well. So that's an example of supervised learning. Again, you know the inputs and the outputs, and you can start to perform some analysis on this, such as classification and regression. Now, another area of focus here, another way to train your model is through an unsupervised approach. And this is where, personally, machine learning gets really interesting for me, and in the industrial space. So you think of, you strip away the labels. Maybe you're exposed to a data set, and you don't quite know what is in that data set. If you train a model with an unsupervised approach, the model will start to identify relationships without any reading on what is necessarily valuable or not, but it'll expose the relationships in that data set so that a human can come in and take a look and start to determine what's important, what's not, what I need to take a look at, and what's less important. So two very different approaches that can be used in different use cases. And this is how you can start to perform clustering on a set of data or some anomaly detection. And I've got a pretty good use case that I'll walk through in a little bit. But any questions so far? That is a real basic overview. A lot of you guys have probably seen this already, but just wanted to do some level setting. So an example of regression is, let's say we've got a collection of sensor data from like a compressor or something. We want to make sense of this data. Well, we've got this for a handful of months, and we want to figure out the most accurate model. So another way, regression is somewhat of a curve fitting practice here. So you start by applying this to your algorithm to determine some representation of this data, right? An easier shortcut at representing this data. But it's still not a perfect approach. So you iterate, the algorithm iterates, does this again, and eventually you have this model that is a more accurate representation of the data without needing all of the data points in this. So you can take this and start to predict future quantities or predict future behavior. Now I'll jump real quickly into the type of classification problem. So similar to the apples, let's say these represent marbles, right? How would you start to look at these? Like, how would you break these down? What are some of the characteristics? Well,
Size.
yeah, size is the one that jumps out, right? So you can look at this, but you don't quite, for an unsupervised approach, you don't quite have any labels on this. So you need to start developing these patterns and these relationships. So you would run this through an unsupervised algorithm, and the unsupervised algorithm would determine which buckets would be important. So it would cluster these in a group that, and probably highlight that, hey, let's start by looking at size. And we can sort these and we can fit these into a pattern based on size. Now let's say we have another dimension such as color. We can start to build buckets around that as well. And the machine learning algorithm will parse this and will classify these into the right buckets. Now, a more prevalent example here is just with data, with another type of industrial data. This is based off of an asset in the field, and we can start to get patterns that come out of this data. Run this through the unsupervised approach, and we can start to, the algorithm and the computer start to identify patterns that make up a decent representation of this data. But again, it's still not perfect. There might have to be several iterations. And at the end of the day, it iterates again. And at the end of the day, you've got this representation of which clusters are important and which outliers don't map up. So this is really important for when you're trying to characterize like the behavior of a machine, where you know that this machine has been operating in a certain way, but maybe something new happens. That would start to appear, that new behavior would start to appear as clusters, and so then a technician or an analyst could go in and take a look and understand what's causing that change in behavior. So that's one way of looking at strictly data to address some of these problems that we're seeing in the industrial space. Any questions so far? Yeah.
So, difference between supervised and unsupervised data. Supervised data, you're looking for a specific value, and it's if this value, then some action.
Right.
But if it's unsupervised, then you're just setting a tolerance. You don't know what the value is going to be, but as long as it falls within that range, then you take action accordingly.
Yeah, no, that's a great summary as well. Yeah.
Yeah, I like analogies, right? To me, machine learning is more like how kids learn, right? When a kid doesn't know what a ball is, you just point to the object, say ball, that's something else, right? So that's like how machine learning does, right? That's the supervised. You just feed a bunch of data. You know, these are all balls, these are all bananas, right? But the unsupervised one is like, you know, you have similar objects, but you don't know what they are. You have a label.
Yeah.
Right? That's basically one difference.
You know, that's a great analogy as well. Like, one other analogy is like, if you're taking a test, right? Like taking a test in school, multiple choice, the teacher knows what the inputs are and what the outputs are, right? And so over time you get better at taking that same test. So yeah, no, great analogy. Any other analogies here in the room?
I don't have an analogy, but just wondering, so why would that far right, the one next to the outlaw on the right-hand side, why would that right one be included in this cluster? Because he seems like he's further out from the other guys. And why did you include him?
Sure, so the intent of this algorithm is to determine the optimal clustering. Now, it runs through the algorithm, and there still may be patterns that don't fit into that. So those outliers are true anomalies. They don't belong in a cluster because the machine has clustered it optimally.
Yeah, but why would you take those two guys on, in between 30 and 40 and 15 and 20, and then the one next to the right of that? Why did you include him in the circle? Because they're not, like, say you're shooting bullets, right? That's not part of my little grouping, right?
Sure.
So why did why did they include that in that particular cluster?
I mean, in particular, I think it has to do with the tuning of the model and the tolerances that they had set there. But yes,
Yeah, this
exactly.
is more conceptual, right? Because it's not going to be a two-dimensional issue. Think of it as a multi-layered issue, right? And as humans, looking at all the data, you can't really know what the relationships are. So based on looking at all these layers, all the information, you just say, you know what? Based on everything I looked at, this data set is good. And just for whatever reason, right, that outlier doesn't fit within that group.
Yeah, because like your cluster circle is a different size.
Yeah, but see, this is simplistic,
Yeah.
two-dimensional, right? So you can't think of it that way. Because the issues are always more complicated, many layers, right? Just like an n-dimensional kind of grouping, right? So you can't really, this is just for illustration purposes. It's not going to be like, oh, I have a circle and a two-dimensional one. So you can't really look at it this simplistically.
So for the clustering, do you set the parameters? Do you feed the machine stuff like, okay, it has to be within this distance of something, or, you know, do you tell it how to cluster, or do you just say, hey, do you just go cluster well you see fit, or do you have to guide it? Or can you do either way? If you do either way, is there a special name for the guided clustering versus the go at it unguided clustering?
Sure, that's a great question. So in the model building process, there is going to be some tuning, there's going to be some parameters that are set to build in tolerances and to build in variation, right? Now, this, you could, so one way that an engineer could look at this, or an SME could look at this, be like, okay, those anomalies aren't really that important to me. They actually belong in the cluster. So through a process of semi-supervised learning where you've got a human in the loop, they could take a look at that and say, no, I understand this is a good representation of the data from my asset, but it's not perfect, and I know from experience that I can actually improve those. And then there's a level of retraining of this model so that for the future, the model knows to incorporate those type of anomalies in. So yeah, it's definitely a learning process.
You just, that example you did with the test, kids, do you have for unsupervised, saying, like, what would that test be for an unsupervised?
Sure, that would be more of like an essay, right? General concepts where checking for the ideas.
You would cluster the ideas that you found in the text together and find relationships between maybe the next essay or something.
Right, exactly. That's great. Yeah, great questions. Any other questions here? Well, just I know it's early on Friday. I know there's data science is everyone's favorite thing. First thing on Friday morning. I've got two more concepts that I think are really important here. And one of this is the concept of explainable AI. So I think one of the things that humans struggle with sometimes with just getting an output out of an algorithmic model, black box, is trying to understand and trying to piece together the logic that came up with this outcome. Because you can have a machine learning model that looks at tons of different variations, different types of data. It looks at tons of variables, and at the end of the day, spits out an outcome. But that's hard for humans to process because depending on the situation, you want to understand somewhat of how the inputs got tracked to those outputs, and that's where explainable AI comes in. Kind of going back to the industrial example of like a heavy asset. One way that this is really important is with an asset, or actually let me use a different example. You guys are all probably had that dreaded moment when you're driving around and you see the check engine light come on, right? You're like, ah, crud, I gotta go get my engine checked. And that's an indicator, that something's wrong. But it's not a complete picture, right? You typically want more understanding of what that means. So if you apply concepts of explainable AI, you would also maybe get a text on your phone or an email saying, hey, the algorithm noticed or the model noticed that temperature reading was a little higher in your engine block, right? There's additional vibration. You've got a piston misfire. So that type of analysis would be in addition to just having that check engine light, which is really important when you're dealing with complicated machines. You want some understanding of why the algorithm gave you that outcome. And with that can inform troubleshooting and can streamline a lot of the downstream processes. Kind of going down this analogy, like think about the repair time, think about the pieces that need to be ordered, think about the technician that needs to go out to fix that asset. There's a lot of other complicated processes that rely on those insights, and machine learning can provide those insights through explainable AI. The other thing I've kind of touched on a little bit is continuous learning, right? These algorithms, these models are intended to learn over time and get better over time. So a lot of times, let's say we've got a legacy way of building a model through like a statistics-based approach or a legacy approach. If the variables change, you have to go back and kind of redo the entire algorithm and the entire model. You have to go re-engineer that. With continuous learning, just like a human would learn how to retake that test or get better at writing that essay, the algorithm learns over time and gets better at solving the problems and gets better at recognizing the data and what's important in the data without needing a human to explicitly program it to do that.
So with continuous learning, I mean, how does it know whether its results or its conclusions that it's offering you is accurate over time? Do you have to go back and say, well, you know, you gave me this reading that there was a 90% chance that a failure was going to happen? Does someone on the human side say, no, that was incorrect, Mr. Algorithm, you need to recalculate, right?
Yeah, no, absolutely. There's typically, for a lot of these applications, a human in the loop that is still monitoring. You don't want to just let this model run necessarily, right? You've got a check and balance to make sure that it's still performing. But like that clustering analysis where you've got that anomaly and you want to reclassify that as part of the cluster, that would be one process in continuous learning. So the more, let's say, the more asset classes that model is exposed to can start to incorporate learnings from different types of variation and the way a similar machine might work.
One question. The question is that we talk about AI, and it's not like you plug in the algorithm and it's going to do all your work for you. If you don't set up the algorithm with the right parameters to begin with, the algorithm is only as good as the parameters that you set up. For instance, if you're running a paint shop and you forget to have humidity in that model, that affects the paint quality, right? So, we're not completely divorced from this artificial intelligence. You have to set the parameters right in the first place. And then the iterative part of the algorithm clues you in on the key areas. Is that correct assumption?
Yeah, no, that's a great summary.
I don't have a question, but just one comment. The key is to make the model as general as possible. Because there's a big danger of making the model overfit the training data, at which point it's not going to be generalizable to unseen data. So there's a concept of bias variance. So you have to find the right mix, and the way to go about it is to get training data from various different aspects so that when it sees an unseen data, it is able to generalize it and have a reasonable level of accuracy.
Yeah, no, that's a great.
Can you kind of summarize what he said?
Yeah.
Folks back.
Yeah, so basically, there's a fear that if the model is too specific, you might have inaccurate results because it's overfitting to the data. So that's what's hard about data science. It's finding this balance between what the optimal approach is to what the optimal parameters and tuning is to get the results that you want consistently. But that's a great point. Overfitting is a problem. So again, data science is all about balancing, tuning, and that's why it's hard and it's complicated.
So how much of human time do you need, like based upon, some of the things you guys have done at your company, how much human capital or time, I guess you would say, do you need to put into it, and do I need to dedicate a data science person, or what kind of skill set, just a programmer, or what is the process of going about correcting the model? Just kind of, how much time does it take, and, is it a...
Sure, I think it depends on the business context, right? So there's one way where, depending on how time sensitive, you could devote a little bit more time. But for instance, go back to the industrial example of monitoring data from really complicated assets. Machine learning makes it easy. It surfaces our solution surfaces the insights and gives the leading indicators for that anomaly. And then a trained SME who's got experience on that asset can actually go in and be like, okay, well, let's classify this, and then with just some configuration based, you don't need a data scientist to reclassify it.
So you guys have simple queries and stuff that's go in and if necessary.
Yeah.
Okay, that's cool.
And then we're building in functionality to be able to continually retrain. So incorporate an anomaly, retrain the model, and then we'll keep that at the model to date.
So how do you guarantee the level of data that you're getting? Because we work with utilities all the time, and their two number one problems is data quality and data access. And what happens if, the early generations of public internet facing IoT devices, those what if those devices slowly go rogue, right? So how can you guarantee, because you're calculating based on the data that you're gathering and taking those points, that data quality is good enough for the AI to spit something that is worth something?
Sure, that's a great question. Data quality is a big component of machine learning. And that's another part of the data science process that is really important. It's cleaning the data, making sure it's scaled correctly, making sure there's not too much missing data. So that is one of the things that has to be taken into account is how good is the data that you have? Is it good enough to apply machine learning to that particular problem? Is I think how you handle that.
What are some of the strategies you use in continuous learning to make sure that the machine doesn't learn the wrong lesson? Giving an example in human learning, if I walk into the bank and my shoulder holstered gun happens to be showing and the teller immediately hands me $1 million, if I make that connection and the police don't come and get me, then I may decide that next time I want to pull the gun out as I walk in, and so you learn the wrong lessons because you're getting positive feedback from a negative example. What strategies do you use in continuous learning to deal with that?
Well, kind of touching back to that's why it's important to have a human, right? A human with the expertise to know when the model's misbehaving, where the model is maybe surfacing false indicators or false positives or things that don't make sense.
Okay.
There needs to be someone there to correct it and make sure that it learns the right behavior. And that's why we're not there at AGI yet, right?
Yeah, like the way I look at it, like way back in time, they had like knowledge-based systems. Like say, okay, like I work in telecom wireless. There's a bunch of different components and things all working to make it work. It's a whole network, short. But so they had like they call it a knowledge-based whatever. So you could Google something. That's like another knowledge thing. You could search for a certain specific keyword to try to learn something or to troubleshoot or to further investigate. So I guess in a sense, AI is sort of like that knowledge-based learning. And it's good because it doesn't throw away all the past data and the past scenarios that came to that data. So it makes it maybe a little bit more efficient and faster to keep learning or to document all the past knowledge. I mean, that's the way I'm seeing it now. I mean, I never thought of it like that.
Exactly. It incorporates all those past learnings back into the model.
Right. Like almost now, if you go to a website or like, I don't know what I was doing, I was looking at my Talbot's perks or whatever. So they had an FAQ, so I wanted to say, well, how does this birthday bonus work? So I would just type in birthday, and then they would give me all these things. But I guess learning it takes it to the next level, right? Because it incorporates all of them. So it does need some learning.
Yeah. Like to that earlier point, that data quality is getting access to the right data and being able to clean it up and use it correctly is key to having a good outcome. Yeah, no, great questions. Thank you all. So that's kind of it for the data science piece. Let's get to the actual problems that we can solve with machine learning and artificial intelligence. Now, at its core, the problem we're solving is with data, right? We have so much data in this world. 90% of the world's data has been created in the last 2 years, and we really struggle to use it wisely. So again, go back to the sensors, we go back to all the documents that are created. There's so much data that it surpassed the human ability to parse through it and find insights. And what that can mean for business is like there's a lot of gold inside that data, right? It can inform business decisions, it can prevent failures, it can prevent catastrophes. Like, there's a lot of important insights and valuable insights in that data. And it's become too hard for humans to accurately get all of those insights. And that's where machine learning comes in. So we look kind of at the machine learning opportunity. There's a lot of text here, but just to summarize real quick, right? There's problems in oil and gas with just prescribing and predicting different techniques for maintenance. Similar with utilities, these are some of those heavy, expensive, complicated assets that are out in the field. How do we protect those and make sure that they are not causing problems? In financial services, we use some of that natural language processing to derive insights out of contracts and find risk. And in healthcare, there's Drug discoveries is one way where we can use machine learning to parse through data and get some insights. Retail, planning logistics, and then transportation. We're dealing with assets and a lot of optimization problems in transportation. Any particular, I've heard telecom in here, we've got some consulting. What other industries are represented here in the room?
Medical.
Medical, great. So a lot of
Agriculture's on there.
I'm sorry?
Agriculture?
Agriculture, absolutely.
I had a question on your website. I went to the website and I saw the little, not fans, windmills there. And it said something like 10% better. It said just 10%. In my mind, it's like 10% against what? Against having absolutely no sensors and no prior, monitoring, or 10% above what? 10%? And then when do you get your return on? Well, that's a different return on investment. So I mean, I kind of left me wondering, what are they measuring against? What was their baseline that they were basing this 10% on? And I don't know if you know about that specific use case example, because it just kind of, to me, if somebody tells me 10%, I want to know, how did they test this? What did they use as their baseline?
Sure.
Before and after. I mean, to me, 10% is like, what? How? I just, so maybe you can go into that.
Sure, so let's take the example of predictive maintenance. Predictive maintenance isn't necessarily new. As long as there's been complicated assets, we've wanted to understand and get some indicators on when that machine is going to fail. But a lot of that relies on human expertise. Humans have set levels and thresholds where when a sensor crosses a threshold, it's indicative that they need to take that asset offline for maintenance. Now, that's one approach, but it doesn't solve the problem of new machines and new situations and changing temperature dynamics and atmosphere. There's a lot of variables that can affect that. So the existing solution is based around that subject matter expertise, and some statistics-based methods of doing that. But machine learning can look at all the different variables, all the different relationships, and all the different types of sensor data at once, and start to truly understand and surface to an SME what is important and why. So what that does is it expands the failure horizon, so you can typically get some indicators and with more advanced notice and plan your maintenance around that. So the comparison, to your point, the comparison is against some of the existing ways of doing it.
Okay, so the existing ways would be just like a sensor going off and you say, oops, I just need to look into it. But with the AI on top of it, it tells you like the root cause analysis, for example. This probably is getting, this rotor's probably running out quicker because the wind's blowing faster or whatever.
Sure.
So it gives you more insight.
Sure, so the traditional methods have a smaller collection of data points. But let's say it's the actual indicator of a failure is like one obscure temperature sensor that starts changing, and that's not known and not aware to the operator. Machine learning would find that even if it just spikes for a very short amount of time, it would say, hey, that's an anomaly. We don't typically see that behavior. Let's level that out.
Okay, but in the long run, if it's saying this is failing faster, they're not really saving money because that means they have to replace it sooner. So if they say 10% increase the ROI for the customer 10%, I mean, I don't know if they can really say that. I mean, I'm just saying that from devil's advocate.
I can address that. The point here is that you're able to predict well before the actual event happens.
Right,
and
because
that saves a lot of money.
Yeah, downtime is bad. Everybody knows that. Nobody wants to have downtime or run out of things you're selling or anything
Speed
like
at
that.
which you fix it, that saves you a lot of money.
Yes, so for example, if you have an oil well out in a remote area, and you're able to know that because of the raise in temperature, which is outside the normal range, that if it's not fixed, that valve is going to blow in 2 days. And that's going to be a huge expense to fix it. But if you knew it well ahead of time, based on the prior data and the AI machine learning aspect of it, you can go and fix it before the valve breaks. And that's a huge cost savings.
And they determine priority as well, right? So you can say, is this critical, or can we actually wait until the next time we do scheduled maintenance to address this, right? So some of that is driving optimization because anytime you take that asset offline, it's not producing.
Right,
So
something.
there's opportunity costs there, and then you have to pay to fix it.
Yeah.
And
Another use case I thought, because I kind of looked into this too a little bit and are thinking about that first, is you can compare machinery. Like say you have machinery from company A and company B, but company A's really lasts longer than you think. Okay, well maybe it's better for the environment company A windmills and B windmills. So I guess if you start thinking of it like that, because I'm looking at it from a holistic point. Because when they say saving you money, okay, yeah, that can be lumped into a lot of different things. I mean, in the end, if something's breaking, somebody's going to have to pay somewhere to get it fixed. But yeah, it is just interesting. I guess the measurement, I guess my suggestion would be on your website, say 10% over existing methods, nothing only sensors. Versus sensors with AI. Because I really think sensors with AI is
sure, I'll bring that feedback.
Yeah. Quite two things.
Well, let's move into some. So we started touching on a few case studies here, but like I mentioned, one of our markets is in the heavy industry. So one of our customers operates as a utility company that operates some of these massive turbines. Like these turbines, these combustion turbines, can be $50 to $100 million. These are expensive, critical assets. So at the best case scenario, they have to take the asset offline to do some maintenance. Worst case scenario, this thing could actually explode. And that's a big problem, that's a big deal. So this utility company was really concerned with trying to understand and better estimate when they were going to experience failures. Now, they've been kind of looking into artificial intelligence and machine learning to solve this problem and applied it to their application. And we actually caught it. So they had delivered they had a new series of turbines. So there wasn't a whole lot of failure data with these to begin with. So there wasn't the in-house expertise to understand the personality of these types of assets. And we actually, through an unsupervised approach, surfaced an anomaly with a 1 month lead time that would have led to a significant failure. So what was actually happening was a little pin inside this turbine had come loose, and one of the fan blades was rubbing against, was creating a lot of friction. And this wasn't caught by their existing method. So this is an example where had that behavior continued, this asset would have been in a really bad shape. And this is a manufacturing problem, so this problem likely never would have happened before. And because machine learning could look at all the variables and understand the entire profile of that asset, it was able to predict something as small as a pin drifting outwards.
Look, you can think of like you're looking for a needle in a haystack, right? So, are you gonna look everywhere in a haystack looking for the needle, or do you use clusters and say, you know what? Maybe it's this little 5% area I gotta look at, and I'll basically narrow down where I'm gonna look, right? So you get efficiency that way, right? So, and that's really what these things do. They don't necessarily tell you what the problem is. They maybe help you focus with the little, right? So that's a savings, right? I can spend 1,000 hours, so maybe I spend 10 hours.
Yeah, or maybe that pin is still under warranty. And somehow you can tell the people, hey, you better fix it under your dollar.
It's more finding out where do I focus, and that's really a great example, right? There's so many issues that can happen with your machine.
So it's like a directed learning.
No, great clarification.
Hey Gabe, for these really expensive assets, to what extent are you seeing these manufacturers using the concept of digital twins to help manage, maintain, predict failures, or are your customers kind of creating their own digital twins?
Sure, so as engineer, our customers are creating their own digital twins. We're not necessarily in that space, but that could be on our roadmap. I mean, it's typically the use case here is we supply they already have some sort of analytics team working with these machines. So we provide them additional firepower, additional layer of understanding of that asset. Now, in this case, like you've got one utility company that is doing this, but you can also look at the use case for that manufacturer, the OEM of the turbines, right? They can start providing, like, if they start packaging machine learning as a predictive type of monitoring tool, they can add more value to their customers and take some of the burden of managing these assets online or on site off their customers' plate. So there's different use cases here for how both a user and like an OEM can apply and package machine learning in a way that drives a ton of value in these companies. Now, okay.
I'm sorry. You said that interface would usually lay as a component inside the client's business?
Right, they would have access, so there's a product called SparkPredict, they would have access to the SparkPredict UI, and they would be able to do some analysis to get the leading failure indicators, that type of thing.
I'm saying they're using it in addition to their existing operations.
A lot of times, yes. Now, I'll switch gears here a little bit to like a natural language processing type application. I didn't spend as much time here, but one of the ways a big aerospace customer of ours is trying to coordinate and perform better maintenance repairs on their aircraft. Right, so they've worked with us to build this model that looks at all the maintenance logs, all the manufacturing data, all of the different instruction on how to fix certain problems with their aircraft, and coordinate it all to a tablet so that their tech can go to the airplane and know exactly what troubleshooting they need to do, and all that information is available much more on an on-demand basis. So this is another application of machine learning where through a process called natural language processing, you can get super critical information in a short amount of time.
What do you do in that case, say with Southwest Airlines? They have, I would almost call it a black swan event, where the fan blade of the engine broke off, blew up the entire engine, and went all the way through the aircraft window, killing the woman. You know, how do you manipulate that data so it can be useful? Because that's something that manufacturers have got hundreds of thousands of hours for those same things. It wasn't something brand new. How do you come up with something like that and prevent it in the future?
Sure, that's a good example of an unsupervised learning approach, right? Or an unsupervised model, where you rarely see those type of issues. But perhaps there was some random association in the data in the sensor data from that engine that could have pointed to that. I know they did some root cause analysis and they couldn't figure out what exactly happens to that turbine, but perhaps with an unsupervised approach, maybe there was some small variable that changed that could have pointed to that type of failure.
The model might be able to see that association.
Repeat that?
Can you repeat that?
I was just saying maybe from a human standpoint, when you're analyzing that data, you might not see the association that caused that failure, when you come back the next time to make that prediction in the future. But this model is able to analyze so much more information, and maybe that model could make that association for you in an unsupervised approach.
Well, okay, I have like maybe a worst case scenario. Okay, like there's always a lemon. Somebody says, oh, buy a Honda, they're great cars. So you buy a Honda and you just happen to have the one lemon that they made. So like for this fan blade, what if it was just that one particular fan blade? And what if the data gathered from those turbines said, oh, this is an outlier, or this is an anomaly, or this doesn't match all the other 30 turbines that we're checking, so let's throw it out, and the lady still dies. I mean, that's all. I don't know if that's always going to be a problem. And how many sensors do you need to put on something? And what's the break-even point between how many sensors do I use and what's it going to find? And I guess that's the scary part about the data analysis. It could throw out that one lemon. It was just, I think, one specific fan blade that was cracked that caused that death and that catastrophe. And it could have just been a lemon. You always get a lemon. I'm sure all of us.
I think the point that I'm trying to make with machine learning is that it can analyze more data, right? So that would be more, you're relying on human error versus something that can provide a lot more analytics around all the different sensor relationships. So you're actually able to process more data and more information to look for those type of really obscure issues.
But with the data, like we were showing the plot where you kicked out the outliers, or it like normalizes data, and I know they throw out some data. Would that have happened? I mean, if that would have happened, that catastrophe would have still occurred because.
Well, the outlier thing that you showed us in a grade, it's not working the way you think it is because you're looking at a snapshot of time. And in machine learning, if it's looking, it says all this stuff is consistent, but like this one time, this is out here, that doesn't make any sense. But there's a consistent demonstration that's out the norm, then it will say, okay, there's something wrong.
Okay, so it's, okay, so,
Like, you have to
like
look
you're
at it from
saying.
you have to look from a whole big picture of mathematics, not just
Not
a
just one
screenshot.
step. Okay, that makes sense.
Yeah.
So then it, like, you keep a tab on it. Okay, that's good.
So I know we've got about 5 minutes here. I'll try to wrap things up. But one way that this can, so the two use cases that we talked about are solving a very specific type of problem. But you start to look at AI a little bit more holistically with a broader lens, and you can start to see how different components of AI fit into a much more comprehensive type of solution. So for instance, let's go to that utility company that wanted to get better predicting their failures in their combustion turbines. So they solved that problem. They're able to predict with more advanced tools. Now it's more, okay, so then how do we expand the scope of that to start looking at all of our different turbines, right? Typically there's a combustion turbine, there's a steam turbine on site. So let's look at more asset classes. Let's look at our fleet holistically. And then trying to actually identify if there's similar behavior in different assets that are on different sites, right? So you start to triangulate some of these insights. Now they've got a more informed approach to perform maintenance, and by using NLP to pull in their maintenance logs and the expertise and the right parts, they can truly streamline a process not just for one particular site, but for multiple other sites. So if you think about machine learning as a solution for one specific problem, there's also typically a scenario where it can solve it uses a more holistic approach for your organization. Now, just a few things that we'd like to start, as you're starting to think about how to use machine learning and artificial intelligence in your applications for your particular problems. Like some of the guidelines that we like to throw out are like, start with really good data. If you've got a problem that has a lot of data around it, start there. That's typically a good candidate. Because if there's a lot of data, typically there's a lot of overhead, a lot of manual overhead at understanding that data. So you combine those two together, and that's a good qualifier for a candidate for a machine learning project. Next thing is like make sure that machine learning is an appropriate solution, right? It may be overkill, may be too much effort if you're just trying to predict different sensor values in the future. But that spot is when there's tons of data and when it's really complicated to extract insights. And then get alignment with your team. There's a lot of different perspectives on AI. We see a tremendous amount of business opportunity from machine learning and AI. And so coordinate that with the team. Who's going to own this? Is this a one-stop type of project, or is this something that you actually want to integrate into your organization? What we're seeing is like this, the pace of this technology is accelerating very, very quickly, right? We're going to be in a completely different space in just a few years. So there is a sense of urgency. The customers who adopt AI and who go through this process of understanding it, and really trying to apply it to their problems will reap the benefits of the technology that's coming in a very short amount of time. Exponentially, exactly. Now, just kind of wrapping up with a little bit about SparkCognition. You know, we excel in natural language processing. We've got a really good process around building these models and can package it either as full-fledged solution or for a way to make anyone who's using data at your company more effective. We provide some really complicated, really complicated algorithms and model building to provide the value that you guys need. And at the end of the day, we can wrap that up in a pretty powerful visualization, so you actually take those insights from that data away. You know, as a company, we've been focused on this vision of not just solving one particular problem in industry, but actively looking at how we can solve multiple problems within one company or an entire industry and reshaping how businesses think about this. So, you know, we've spent a lot of time, a lot of effort collecting a fantastic bunch of team members who have expertise across a variety of industries. We've got deep subject matter expertise, so we can typically talk the language of our customers and understand their problems because it's likely that someone on staff has felt those exact same problems. You know, we're really committed to making sure that explainable AI is forefront, right? That you know that you're not just getting this black box algorithm that's going to provide you an outcome. You actually understand why it is doing that. And then same time, we're actively trying to accelerate this technology, right? We're looking into stuff that's not been done before and how to use that to make our customers even better. And we do that, we wrap this all up, we do that with advanced machine learning algorithms. They're really, really advanced proprietary model building approach to create high-value solutions for our customers. Now, we play in a variety of industries. We have 4 key products, so instead of just having a solution, try to productize as much as possible of these solutions so that it's more turnkey, or it's more accessible for you guys as customers. We have the predictive maintenance product. We have a cybersecurity product that uses machine learning to understand and evolving malware threats and better provide insights on how to remediate those. We have an NLP product that can source and make sense of unstructured data. And then we have this Darwin product, which is helping to bring anyone who's using a lot of data the capabilities to start building models on their own and start to do some of the data science process in-house. Now, we're across a variety of industries: energy, oil and gas, finance, defense, telecom, manufacturing, automotive, mining, aerospace, and others that are emerging. And we're really focused, we're laser focused on solving problems with predictive maintenance, decision support, so extracting insights from data to make really valuable business decisions or justify a business decision. Workflow automation, some of this concept around making the repair process or the root cause analysis process as easy as possible through unstructured data. Input protection, protecting against new malware threats, that deep armor point there, and then optimizing processes. There's a ton of value here if we can solve these applications for our customers. And that's how some of the biggest names in the industries are already working with us. They have adopted AI and they're actively trying to work on this journey and weave AI through the fabric of their organization. So that said, my name is Gabe Prado. If you have an AI problem or question, or if you're just looking to make sense out of more data, let's chat afterwards. Find me on LinkedIn. And I know we've got a giveaway as well.
Right, okay. So let's give him a hand. So if you haven't put your